Hi everyone. In this video, we're going to talk about different ways of showing that an improper integral converges. And then later on the second part in the same video, we'll talk about convergence of series. It's kind of a similar method, and this is the method of comparison. Okay, so comparing what we're trying to study with a different thing that's a little simpler. Right, so we're going to start by discussing convergence of different integrals. And the question is how to tell that an improper integral converges if you can't find the antiderivative of the integrand. Right, so most of the times when we're trying to figure out if an integral converges or not, it was something that we could, integrate by hand, right, compute an antiderivative, and then we would just look if the antiderivative would converge or not, taking the limit. But there's some functions that we can't take an antiderivative of very easily. So for example, does this integral here right? Converge, sorry. So this function is actually a very famous function, e to the negative x squared. It's called the Gaussian function. It's very important in, probability and statistics. The normal distribution kind of looks like this function, a little translated and scaled, but and showing that this integral converges is not very easy. In particular, it's actually known, it's proven that you can't, using the classical functions that we know, you cannot compute an antiderivative of this function. Right? So there's no formula for the antiderivative of this function, and so you might want to, if you found the antiderivative, then you could say, right, this is the limit as b goes to infinity of the integral from 0 to b of e to the negative x squared dx. And if we knew what the antiderivative was, then this would be, if the antiderivative is f, say, so it would be f of b minus f of 0. And it's like, oh, and then you just see if f of b converges or not as b goes to infinity. But we can't figure out what this function is, the antiderivative of e to the negative x squared. And so we need to find another way, right? It's not going to work like this. We need to find another way of figuring out whether this converges or not. Okay, maybe I should leave that. I'll leave it. So, but the question is, will this converge, right? So the idea is we can compare the integrand, so this function, to a simpler function, and that we know maybe converges, and try to compare them. Okay, so here's the theorem. It's a pretty simple theorem, the comparison theorem. If you have two functions, f of x is, so they're defined for x greater or equal to a. A is just some fixed number. If you know that f is always bigger than g, and these are two functions that are positive, they're always bigger than 0. But if f is always bigger than g, then what you know is that if the integral of f converges, then the integral of g, the function that's smaller, must also converge. And if you know that the function of g, the integral of g of x diverges from a to infinity, then this function that's bigger the integral must also diverge. Right? So the idea is just this picture here, right? So if you have a function f and a function g defined from a to infinity, and you know that g is always below f, this is this condition here, right? That g is always smaller than f. Then, statement 1 says, if the integral of f converges, then the integral of g must converge. That's because if the integral of f from a to infinity converges, then if the area under the blue curve is finite, well, the green curve is always below it, so it must be finite as well, right? So this is what this is saying. If the integral of f converges, the integral of g must also converge. And conversely, if you have the situation where f is always above g, if you know that the integral of g of x from a to infinity diverges, so if you know that this green area is infinite, then it must be the case that the area under the blue curve is also infinite, because it has to be bigger than the area under the green curve, right? So if the integral of g of x diverges, the integral of f of x also diverges. Okay, so this is how we can switch our function for a simpler function, right? So maybe you're trying to prove that, the integral of g of x converges. And what you can do is, well, if I know that g of x is smaller than a different function, f of x, that is simpler, the formula is simpler, and I know that this integral converges, then by this comparison, I know that the integral of g would converge as well. Well, let's use this in an example to see how it looks, right? So does this integral converge, the one that we were talking about, the Gaussian? And so what you can, all right, so you need to try to compare this to a simple enough function. And in fact, it's a little bit hard to find this function from 0 to infinity, but what we know is for x greater or equal to 1, it is true that x squared is always it's bigger or equal than x, right? So if for a number that's greater than 1, if you square it, it becomes bigger, right? Well, that's cool. If this is the case, then we also know that if you take negative signs, then negative x will be x squared will be smaller than negative x, right? Because if this number is bigger than that, now if you take negative signs, then this number is smaller than that, right? It's bigger in absolute value, but it's a smaller number because it's bigger and more negative, right? Yeah, and because the exponential function is an increasing function, if you take exponential on both sides, it doesn't change this inequality here. So e to the negative x squared is smaller or equal to e to the negative x, right? So here's our situation. We're in the same situation as before, where we have a g and an f, right? So our let me get a green here. This would be a g of x, and this would be a f of x, right? So our complicated function that we can't quite decide whether it converges or not is bounded above by a function that's pretty simple. This we can take an antiderivative of, right? So the one problem is that this estimate, this comparison, is only valid for x greater or equal to 1. But that's fine. You just break up the integral, right? So first we find that the integral from 1 to infinity of e to the negative x squared dx. So this is not the one that we're looking for, but I'm going to use the comparison from 1 to infinity. That's when it's valid, right? So because this function is smaller than that, then this is smaller than the integral from 1 to infinity of e to the negative x, right? But this we know is the limit as b goes to infinity of the integral from 1 to b of e to the negative x dx. The antiderivative here is minus limit as b goes to infinity. The antiderivative is negative e to the negative x, so it would be negative e to the negative b plus e to the negative 1. And when b goes to infinity, this number here goes to 0. You're just left with 1 over e, right? So this integral converges, which means that this integral here must also converge. Let me scooch some things here. Try to fit everything into the space that I gave myself. Ugh. Let's see what I can do here. Yeah, so so usually the hard part of solving these problems is figuring out, like, okay, what is the simpler? It's getting this part here, right? What is the simpler function that I can compare my function to, right? And the goal here was just like, well, it's e to the negative x squared. Maybe I can turn that into an x, right? So that's kind of what motivated this little part. But then once we were able to bound it above by a function, and we know that this function e to the negative x, the improper integral from 1 to infinity, converges, we can figure out that this integral converges of e to the negative x squared. And the one that we were really looking for is the integral of e to the negative x squared from 0 to infinity But this is equal to, you can integrate from 0 to 1 plus from 1 to infinity. And this is not an improper integral here. This is integral from 0 to 1. We know that there's no convergence issue. It can't have infinite area. This really is the issue. Does this converge or not? And we know it does from our comparison, right? So this is not improper. You might call it proper, perhaps, but we don't really, right? This is not improper. This is a finite number. This is an improper integral, and we know that this converges, right? So the answer is yes, that integral converges. All right. So that's one way that you use the comparison test, right? You try to decide whether an integral converges, and you find either, then you need to have some intuitions like, will this converge or not? And you try to compare it. You just try to make it a little simpler, right? So you compared it. You can either show that there's a simpler function above it which converges, and that will imply that this function converges, or you can find a simple function that's smaller than it, right? And if you know that that diverges, then this integral will diverge. There's a little bit of thinking there that you need to do. One little interesting anecdote I'll just tell you. Even though we can't compute the antiderivative of this function, we can compute this integral explicitly, actually. Not in this class because it involves techniques from vector calculus, so your next calculus class. But this integral is kind of cool, actually. It's equal to square root of pi over 2. So you're integrating this e to the negative x squared. It has an e here, but then when you integrate from 0 to infinity, it's a square root of pi over 2. It's kind of cool. It's a really neat thing to try to compute. It's a little too early for us, though. So in your vector calculus class, you can ask your professor to show this to you. All right, let's do one more example. Example 2, does this integral converge? 1 plus e to the negative x over x. So again, you can try to find an antiderivative for this function by hand, and you might be able to, perhaps. I'm not sure, but it's not easy. But the easy thing to see is that, well, 1 plus e to the negative x, this is always a positive number. So 1 plus e to the negative x, well, okay, let me, not to be too abstract. You look at this and you go, I feel like this, I think this does not converge. Why? Because I know that 1 over x doesn't converge, right? We already talked about this function. The antiderivative is ln of x, and when this goes to infinity, that is infinity, right? So this integral doesn't converge from 1 to infinity. It won't converge. And so I go 1 plus e to the negative x over x, that's even bigger, right? So 1 plus e to the negative x, that's 1 plus a positive number. So this is bigger than 1, and so this divided by x is bigger than 1 divided by x. So if that's the case, then the integral from 1 to infinity of 1 plus e to the negative x over x dx is greater or equal to the integral of 1 to infinity of 1 over x dx. And this we know diverges, right? So this must diverge as well. So no, it diverges. All right, so this is the comparison test for integrals. I think the next, yeah. So the comparison test for integrals is, can you tell whether an integral converges or not? And you do that by trying to compare the function that you're trying to integrate with a simpler function that is either bigger or smaller than the function that you started with. A simpler function that is bigger if you think this integral is going to converge, or a simpler function that is smaller if you think that this integral is going to diverge. Okay, so there's a little bit of wiggle room for you to decide what is the simpler function, but that's how it works. Now, for a series, this is actually a little bit easier. So let's now discuss the convergence of series. Right, so we can use a similar strategy to determine the convergence of certain series. So our first example will be, does this series here converge? Right, so the sum of the reciprocal of the squares, right? So sum of 1 over n squared. This is, if you write it out, just so you have a picture of what's going on, this is 1 plus, right, n equals 1. N equals 2 is going to give you 1 over 4, 1 over 9, 1 over 16, right? 1 over all the squares. I made a little note here. Oh, sorry. Actually, let me get back. I'll come back to this. Let me get back to the integral. One thing that I wanted to point out is that this method can tell you whether this integral converges or not, but it cannot compute the value of the integral for you, right? So we still don't know. So this we know that it diverges, right? So it's infinite area. But for example, over here, we could figure out that this integral converges, right? It gives you a finite number, but you cannot compute what the number is, right? This method does not let you compute the integral. It just tells you whether it converges or not, right? So we know, I was telling you that the value here is square root of pi over 2. Computing this integral is a whole other business, right? But this method lets you tell whether it converges or not. Okay, so that's a distinction that you need to make in your mind. So this is asking you, does it converge? It's not asking you compute this integral, right? So similarly, the problem for series will be the same. Like our strategy will allow us to tell whether this series converges or not. But computing it is a completely different business. And in fact, that's the historical remark that I wanted to make. Computing the value of the series, 1 over n squared, is called the Basel problem. And it's a very, very famous problem in mathematics, and it developed a lot of interesting mathematics. This problem was posed, at least, in Europe. I don't know. Math history tends to be centered in Europe. But so one of the first times, I guess, this problem was posed was in 1650, so quite a while ago. What is that? 370 years? So it's an old problem. It was posed in 1650, and it was solved by Euler almost 100 years later, in 1734. So Euler was the first person that was many people tried to compute what was the value of this series here, and many people have failed until Euler figured out a way. There were some gaps in his computation, but they have been fixed, and his strategy actually works, his original strategy. And he computed that the sum of 1 over n squared is equal to pi squared over 6. Pretty nuts too, right? You're summing all these rational numbers, and then you get pi squared over 6. So this is called the Basel problem that Euler solved. It's called the Basel problem now because Basel is the city that Euler was from. It's a city in Switzerland. And solving this problem is actually what made Euler famous. He became a very, prestigious mathematician after he was able to solve this problem. So, you see his name everywhere, and this is kind of his math beginnings. In any case, we're definitely not gonna compute this series in this class. It's interesting though, because the class that I just taught on Spring, that was 105B. It's advanced mathematics for engineering. We computed the series. We learned some methods to compute a series like that. So that was fun. Maybe some of you will take 105 at some point. You can solve the Basel problem. Okay, so how to tell that this series converges? right? Um, so the idea is to compare this series with a given function. Okay, so you see that we're trying to sum 1 over n squared, right? So the idea will be to compare this series to the integral of the function 1 over x squared, right? So now it's a function. X can be, it's just a real variable. It can be any number. It looks a little odd. Let me rewrite that. 1 over x squared. And here's the picture of what's going to go on, right? So here's the graph of 1 over x squared, right? And then you tick here on the x-axis all the integers. And then you draw a rectangle where you start here. So 1 over x squared, right? So what we know is that the integral of 1 over x squared from 1 to infinity, we have studied that improper integral, and it converges, right? We know that 1 over x to the p will converge from 1, the integral will converge from 1 to infinity as long as p is bigger than 1, right? So for 2, 1 over x squared, it will converge. So there's finite area here to the right. Okay? And so the idea is to try to fit our series inside, right, under the curve of this graph, because we know that the graph has finite area, right? So this is what we do here in this picture. You take all the integers, and then you just draw, you go up and you draw, and then you go to the left so that you stay inside, right? So you stay under the graph, right? So this is going to give you height of 1. Since this is f of x equals 1 over x squared, when you plug in x, this is going to be 1. Oops, and when you plug in 2, that's going to be 1 over 4, right? 1 over 2 squared, and so on and so forth. So the areas of these rectangles, the base is always 1, right? And the height will be f of x. So the area of the first one is 1. The area of the second one is 1 times 1 quarter. The area of the third one is 1 times 1 over 9, 1 over 9. And so when you add up the areas of these, you get the series that we want to compute. And by this picture, this series must be smaller than. Now, you don't want to compare this to, you could say that this is smaller than the integral from 0 to infinity of 1 over x squared. Right? The picture looks like this, right? All these areas are smaller than the integral from 0 to infinity of 1 over x squared. But this is not good because if we integrate all the way to 0, we know that there's infinite area to the left here, right? We studied that. So instead, you ignore that first term, 1. So let me scooch. You know that this is smaller or equal than 1, that's the first rectangle, plus, now all the other rectangles you can bound by the integral from 1 to infinity of 1 over x squared dx. Yeah? So we needed to ignore the first rectangle. This is pretty subtle, so I'm trying to explain slowly because I remember being very confused and doing this wrong when I was trying to understand these things. So you could compare all these rectangles to the integral from 0 to infinity of this function, but that would be an infinite integral, right? Because from 0 to 1, when you integrate 1 over x squared, that has infinite area. So it's not a good bound. You're not going to show that this is finite if you say that this is smaller than infinity, right? So what you do is you ignore the first rectangle. That's that 1. Leave it there. Now all the other rectangles, 1 over 4 plus 1 over 9, 1 over 16, you can bound those areas of those rectangles by the integral from 1 to infinity, right? And now this integral we know converges. 1 is a finite number, so this is a finite number. So the series converges, right? It can't go to infinity. The series sum from 1 to infinity of 1 over n squared converges. That's the comparison method, right? So you look at your series. Basically, you turn your n into an x, and then you look at that function, and you try to bound your series by the integral of that function. So it's a little bit similar to what we did right before with the integrals. You had a complicated function and you compared it to a simpler function and you compared the area of one graph to the area under the other graph. Now we have a series, and then you kind of want to think of the series as the areas of a bunch of rectangles with base 1, basically. And then you can compare the areas of those rectangles with the area under a certain graph that we can try to understand, right? That's the method. The idea is pretty simple. Let's work on one more problem or a couple more examples to see how this works. Okay, so does the series of 1 over square root of n converge? Okay, so we're going to compare with the function f of x is equal to 1 over square root x. Now, what do I know about this function? I know that for 1 over root x, this is 1 over x to the p with p equals 1/2. And if you remember for this function, that wasn't a good picture. For this function, the area here to the left of 1 is finite, but the area to the right is infinite. So in particular, the integral from 1 to infinity of this function here is infinite. And so my suspicion is that this series is going to diverge, right? Because this function has infinite area from 1 to infinity. Let's make that a little bit more rigorous. So we'll have to draw a picture that I have already drawn. Didn't want to waste too much time here. Right, so I drew exactly a very, very similar picture, but not exactly the same, actually. So here's the graph. This is the graph of 1 over root x. Maybe I should write it. Y equals 1 over root x. And now again, I ticked the integers, but as you see, I went up, and instead of going to the left, I went to the right, right? So that my rectangles are above my graph. Okay, so I went up and then to the right, so that my rectangles is above my graph. Why? Because I know that the area under the graph is infinite, and so by this picture, the sum of the areas of the rectangles is going to be infinite, right? So I'm trying to get a lower bound, basically, instead of an upper bound. Let me compare. I'm going to scroll up so you see the difference, right? So because this function, the integral diverged, really I'm going to compare my series saying that this series is bigger than this integral, and that's why I went to the right, to say that these rectangles, they add to more area than the area under the graph. While before, this integral here converged, right, from 1 to infinity, and so I was drawing my rectangles, I would go up and then to the left so that I would stay under the graph at all times, because I wanted to say that my areas were smaller than the areas under the graph. Okay, so it's a little bit different depending on whether it's going to converge or diverge. But okay, the area of the rectangles, again, the base is always 1. So the first area is going to be 1 times 1, right? Because this is 1 over 1 root 1, which is 1. Now the height of this rectangle is 1 over root 2, right? You plug in x equals 2 into this function. So it's 1 over root 2 times 1, 1 over root 2, 1 over root 3 times 1 gives you that, right? So these are the areas of the rectangle. And from the picture, you can see that these areas are bigger than the integral from 1 to infinity of 1 over root x, right? The area of these rectangles are bigger than the area under this graph, but we know that this is infinite. It diverges. We already analyzed that previously. Which means that this here also needs to diverge. Okay? So I guess the answer is no. The series sum n equals 1 to infinity 1 over root n diverges. All right, so I think the next step Oh, there's one more example that I'm gonna, yeah, one more example. Okay, so hopefully that makes sense. Wait, don't want to move too fast, so hopefully everything made sense, right? So drew my rectangles expressing my series as areas of rectangles and compared it to this function. The integral of that function was infinite, so the areas of the rectangles must be infinite as well. Okay, one more example. Does this series converge? So again, we compare with f of x equals 1 over 1 plus x squared. Okay, so this function, the antiderivative is arctan, right? And arctan, as it goes to infinity, is pi over 2. So this is going to converge. And so I have my picture here. I'll do the same strategy as before. I put my rectangles under the graph of that function. Right? So this graph is y equals 1 over 1 plus x squared. And from this picture here, you can see, and now you can integrate. Remember that before I was like, don't integrate from 0 because there's infinite area from 0 to 1, and that would mess you up. Well, now that's not the case. There's finite area here, so you can actually compare from 0 all the way to infinity. Okay, so this series, the areas of the area of rectangles, it's x equals 1, you're going to get 1 over 1 plus 1 squared, so 1 over 2. So the first one is 1 over 2. The second one, plug in x equals 2 into your function. 1 over 1 plus 4, so 1 over 5, plus. Plug in x equals 3, 1 over 1 plus 9, it's 1 over 10. X equals 4 is 1 over 1 plus 16, so 1 over 17. From the picture, you can see that the areas of these rectangles, right? So I went up and then to the left because I wanted to stay under the area of my graph because I knew that the area would be finite. So this is smaller than integral from 0 to infinity of 1 over 1 plus x squared dx. Now I just need to analyze this integral here. So that's limit as b approaches infinity of the integral from 0 to b of 1 over 1 plus x squared dx. Antiderivative, as I said, is arctan. So this is arctan b minus arctan 0. Arctan of 0 is 0. Right? Tangent of 0 is 0. Okay, so this is equal to 0. And arctan of b, as b approaches infinity, let me draw, I think I drew this picture before, but you can draw the unit circle. And if you want to know tangent, you draw this tangent line here at this point. If you draw an angle theta, this distance here is tangent of theta. And arctan does the reverse, right? It takes a point here, b. Arctan will associate what angle it gives, right? And as b goes to infinity, the angle goes to pi over 2. So as b goes to infinity, arctan of b converges to pi over 2. The important thing is, there you go, this integral is finite, so this series must converge. So yes, the series sum for n equals 1 to infinity of 1 over 1 plus n squared converges. All right, so I wrote here a theorem that kind of summarizes this idea, right, of putting the squares under the graph. So the theorem is this: if you have a function f of x which is defined from 1 to infinity. If you denote by an just f plugged in at the integer n, then if the integral from 1 to infinity of this function converges, then the series will converge. And if the integral from 1 to infinity of this function diverges, then the series will diverge. All right? So it basically connects the convergence of the series to the convergence of the corresponding function. Cool, so that's the theorem. We can apply it to do our last example. For which values of p will this series converge? Also, we know that this is related to so this series, n equals 1 to infinity, by the theorem we just wrote. Converges if and only if, so it's equivalent, this integral from 1 to infinity of 1 over x to the p dx converges. And here, this thing we have done already, right? We know that this integral converges when p is greater than 1, right? That's when this integral here converges. So that's when that series converges, right? For which values of p does the series converge? For p greater than 1. That's the answer. 1 over np, right? That's this is called a p series, by the way. It has a name. Not super important, but it's called a p series. 1 over n to the p. All right, so these are the comparison theorems. We learned how to compare a complicated integral to a simpler integral, and we learned how to compare a series to the integral of a function. And that lets us know whether something converges or not. Okay, well, I'll see you in the next video.